All right, so this week in our support course, we're going to be working on solving inequalities. In both section 3.1 and 3.2, which we're doing in the parent class this week, we do a whole lot of this using both our first and second derivative tests. So this is just to get a little bit of practice on solving inequalities that are a little bit more complicated than a linear inequality. Those are the easiest types. You solve those in like a first algebra class, elementary algebra. More complicated inequalities are left to like an intermediate algebra, or you might call it a college algebra course. And that's really the thing that we're going to be dealing with in the parent class. So let me start with this first one. We want to solve this inequality, and notice we want to give our answer in interval notation. So this inequality is an expression that's represented in factored form, and it's greater than 0. So the key thing here is when something is greater than 0, that means that it's positive. So I want to think of this as how to make this expression on the left positive. And the key there is going to be to remember how multiplication of positive and negative numbers work. So remember, positive times positive is positive. Negative times negative is still positive, but positive times negative is negative. So in other words, if you multiply two numbers that have the same sign, which means both positive or both negative, the answer is always positive. If you multiply two numbers that have different signs, then the answer will come out negative. We're going to use those ideas to deal with inequalities like this. So the first thing I want to do is see what this would look like if I set things equal to 0. If I wrote x plus 1 times 3x plus 5 times x minus 10 equals 0, what would the solutions be? Now I'm gonna not write this in the remaining examples. We're gonna kind of just do this mentally, but for this first one, I want to just show what that's equal to. So we're going to use something called the zero product property, which is a really, really useful property from algebra. And basically what it says is that if you have a product of expressions or numbers or whatever it is, and that product is equal to 0, then at least one of those expressions or numbers or whatever it was had to have been equal to 0. So if this is 0 and these two numbers are not 0, then the product is still 0, or whatever combination you want to use there. So basically what I would be doing is taking each of these expressions, x plus 10, setting that equal to 0, and seeing what x would have to be. 3x plus 5, set that equal to 0, what would x have to be? I had x plus 1, not x plus 10. Let me change that, x plus 1. X minus 10 equals 0. Solving these will give me all possible values of x for which this product will come out to 0. And this gives me the following three solutions. X plus 10 equals 0 gives me x equals negative 10. 3x plus 5 equals 0 gives me x equals negative 5/3. And then x minus 10 equals 0 gives me x equals 10. Oh, I did it again. Should just be negative 1. I don't know why I can't get that one right. So this is an excessive amount of work for a problem like this. In an Algebra 1 class, you would need to do all of that work because you're learning it for the first time. In a calculus class, you should be able to look at this and immediately see these answers. That you should not be using this much time to do this work. I'm only doing this for this very first problem. But what we're going to use these values for is to put them on a number line, which will partition the number line up into intervals. So of these three values, the smallest one is negative 5/3. Negative 1 is next, and then 10 is next. I am not at all concerned about spacing these accurately. Negative 1 is far closer to negative 5/3 than it is to positive 10, but I don't really care about that. Scale is not important for this. What is important is that with these three numbers, we have divided the real number line up into 4 subintervals. And in each one of those subintervals, I want to determine if this inequality is true or not. So in other words, I want to determine, is the product of these values within this interval positive or is it negative? So to do that, I look at the intervals that I have created here, and I choose test values. So for example, x equals -10. That's a number that's less than -5/3, so it would live in this subinterval over here. If I plug -10 in for the x's here, does the result come out to something positive or something negative? Don't waste time trying to figure out the exact value that you get by plugging -10 in, because the value itself is not important. It's just whether it's positive or negative. So I'm going to talk you through how we do this. Plugging a -10 in for x here, -10 plus 1 is negative. It's -9, but more importantly, it's negative. Plugging a -10 in here, I get -30 plus 5. Definitely negative. Okay, so I have a negative and a negative. Here I get -10 times minus 10. That's a -20, so definitely a negative number. All three of these come out negative. So when I do the multiplication, negative times negative is positive. Positive times negative is negative. So here, my expression comes out negative, which would be less than 0, and that is not what this inequality is looking for. So we are not going to include that interval in our solution. Between -5/3 and -1, we need a test point. X equals -4/3 is in between there, so I can plug that in. -4/3 plus 1, that's a negative number. If I plug -4/3 in here, the 3's would cancel, and I get -4 plus 5. That's +1. So positive. I have negative and positive. Here, -4/3 minus 10 is negative. So I have a negative times a positive times a negative. That is positive, which is what we want. So I'm going to put a check mark to indicate that that interval is part of our solution set. Between -1 and 10 is the number 0. That's generally the nicest number to plug in, so we choose 0 when we can. Notice plugging 0 in for the x's here is going to give me a +1 here, a +5 here, and a -10 here. Positive times positive is positive, times negative is negative. We don't want negatives, so I don't include that in my solution set. Finally, I need a test point here. I can pick any number that's greater than 10, so maybe x equals 100. Doesn't really matter, just needs to be bigger than 10. And you would see if you plugged 100 into each one of these expressions in this, or each one of these factors, you get positive, positive, positive. All positives means the product's going to come out positive as well. So I have two solutions, or two intervals in my solution set, and I'm going to put them I'm going to use a union to put them together. So -5/3 to -1, notice that interval is right here, union 10 to infinity. That's the other one. It's important that you use open intervals, not closed intervals, because if I use closed intervals, then I'm including these endpoints here, but those endpoints are where this was equal to 0, not greater than 0. I would only use a closed bracket if this was a greater than or equal to inequality sign, which we're not going to use that here because we're not going to use that in the parent class either. So always open intervals for what we do here. All right. Let's take a look at another problem. So this one is 4e to the -2x, 2x minus 20, log base 4 of x minus 16 is less than 0. Okay? This is also in factored form. So I'm looking for those values that I want to put on my number line. So if I were to take this and set it equal to 0, again, I could use my zero product property to solve for the values that are going to go on my number line. Now, exponential functions always come out positive. Doesn't even matter that there's a negative in the exponent. It still gives me a positive number no matter what I plug in for x. So it will never come out negative. It will never be equal to 0. So if I'm looking for where this expression is equal to 0, I can move past that factor and then go to here. I know that if I plug a 10 in for x, that would give me a 0 in that term right there. So I know 10 belongs on this number line. Here, log base 4 of x minus 16, if I set that equal to 0 and solve it, that one, because it involves a logarithm, might require a little bit more work. Log base 4 of x minus 16 equals 0, which means log base 4 of x equals 16. And remember the way you think about logarithms, 4 to what power is equal to 16? Well, 4 squared is 16, right? Oh, you know what? I have this in the wrong order, though. Sorry, I should be saying 4 to what power? 4 to the 16th power, sorry, is equal to x. So that's actually a gigantic number, 4 to the 16th power. So I'm not going to bother writing that in like decimal notation. I'm going to leave it in the form 4 to the 16th power. Okay. Now, I have 3 subintervals to work with. So one thing that I also need to remember is that logarithms are not defined for negative numbers. So there's also a boundary down here at 0. I can't plug 0 into this expression. So let's pick some test points and do what we did before. If I can't use 0, I could use x equals 1. That's between 0 and 10. And if I were to use that, then plugging that into here, remember this is always positive, so we can kind of ignore it and just pay attention to what's going on with these two terms. If I plug a 1 in here, I get 2 minus 20. That is a negative number. If I plug a 1 in here, log base anything of 1 is 0. Minus 16 is negative 16. So I have negative times negative, which is positive. And again, the fact that this is positive means that won't change. So I get positive. We're not looking for positive. We're looking for negative. So this is not part of my solution set. Okay, now let's pick something between 10 and 4 to the 16th power. 4 to the 16th power is massive. So you can pick something like x equals 100, and that's definitely in that interval. Again, this will come out positive no matter what. 2x minus 20, that's 200 minus 20 when I plug 100 in, positive. Here, log base 4 of 100 minus 16. Remember, the logarithm function is an increasing function. It looks like this. And our exponential function is also an increasing function. So I'm plugging in a number that is smaller than 4 to the 16th here, which means the answer is going to come out to something much less than 16. So when I subtract them, 16 is larger. That gives me a negative number here. So now I have positive times positive, which is negative. That's part of my solution set. By a similar token, if I plug in a number that's larger than 4 to the 16th power, say 4 to the 17th power, then I get positive everywhere. Again, this would be a gigantic number minus 20, so that's definitely positive. Here, if I plug 4 to the 17th power in here, I would just get 17 minus 16. That's also positive. We don't want positives. Okay, so from my number line here, the only solution that I'm getting is 4 to 4 to the 16th power. Or sorry, 10 to 4 to the 16th power. Okay? That is my solution for that one. Let's try another one. So number 3, I want to do a problem that involves some factoring. So what if I have x squared minus 8x plus 15 is greater than 0. This time, my expression is not factored for me. In the last 2 examples, it was factored for me, and I needed it that way to analyze this inequality the way that I did. So that's not a problem. You just factor this. This factors down to x minus 3 times x minus 5, and again, we want this one to come out positive. Okay? So I have greater than 0 there. Now, that would give me 2 values where if I set this equal to 0, that this would come out to 0. And that's going to be at 3 and 5. So I put those on my number line. And then I do the same process. If I pick something over here like x equals 0, then I have negative 3 times negative 5. Negative times negative is positive, and that's what we want. So positive. What about something between 3 and 5? Say x equals 4. Well, 4 minus 3 is negative, but is positive, but 4 minus 5 is negative. So positive times negative, not what I want. Finally, pick something larger than 5. Say x equals 1,000. Doesn't matter what it is, but 1,000 minus 3 and 1,000 minus 5, both of those are positive, so their product is positive. Boom. I have my solution now. Negative infinity to 3. Union 5 to infinity. That's the 2 check-marked subintervals. Let's do one more example. We'll jump to a more complicated one. And then I think we have enough here. Let's do this. 4e to the negative 0.8x to the 6th power minus 64e, there should be an x there, negative 0.8x, e to the negative 0.8x, x to the 4th. That's what it is. And we'll make this one positive as well, so greater than 0. Okay? This one looks complicated because we have both power functions like x to the 6th and x to the 4th and exponential functions in there. What we want to do is recognize that there are two terms in this expression and we want things to be factored. So I'm going to look for a common factor that I can pull out of here. I can pull a 4 out of both of these terms. I can pull an e to the negative 0.8x out, and I can pull an x to the 4th out of each term. What does that leave me with? Well, I would have an x squared there. That's all that's left. And over here, the exponential and the x to the 4th factor are gone. I factored a 4 out of this, which would leave a 16 behind. That's greater than 0. But I can go one step further because the expression in parentheses is a difference of squares. 0.8x, x to the 4th. That would factor to x plus 4 times x minus 4. It's greater than 0. So now I have a fully factored expression. I can start looking for zeros and put them on my number line. This exponential function, like we said before, is never equal to 0, so we can ignore that. X to the 4th, if I set that equal to 0, then 0 is how I would get a 0 from that. And then here, negative 4 and here, positive 4 would give me a 0. So negative 4 and positive 4. Those are going to partition my number line into 4 subintervals. And I'm going to look at the results in each one. So let's pick maybe x equals negative 100 in this subinterval. Again, we can ignore the exponential function because it'll come out positive no matter what. But if I plug a negative 100 in here, the fact that I'm raising this to the 4th power means this will also come out positive no matter what. So positive times positive is always positive. That means when I'm checking these test points, all I have to focus on is these two terms. Negative 100 in either one of these will come out negative. So I have negative times negative, which is positive, and that's what we want. Pick a test value in here. Say x equals negative 1. Remember, all this stuff out here will be positive no matter what. So when I plug a negative 1 into these two terms, I'll get a positive number here, but a negative number there. We only want, or that positive times negative is negative, which is not what we want. Now, between 0 and 4, I pick a test point, x equals 1, for example. 1 plus 4 is 5, that's positive. 1 minus 4 is negative. So I have, again, positive times negative, not what we want. And then finally, I have this last guy here. I can plug in maybe x equals 10. That's bigger than 4. 10 plus 4 is positive. 10 minus 4 is positive. I have positives all around, so the product is positive. That's what we want. That means the solutions to this are negative infinity to negative 4, union 4 to positive infinity. Okay, hopefully that gives you enough to go on in order to do the work that we're going to be doing in the parent class.